All right, and thanks everyone for coming. We'll probably have a few more people filter in the next few minutes here. Thanks for coming to the June edition of the Distributed Systems Reading Group. This month, we took a look at making CRDTs Byzantine fault tolerant, which is a very recent paper, just a couple months old, by Mark and Kleppman. As Mark and Sean just mentioned, I'm actually going to see Martin tomorrow for lunch. I just happen to be passing through the UK. He's not able to make it. He sends his regrets, but if there's any questions, I'm going to make sure that those forward those on to him after. In case Martin watches this later, hi Martin, we're going to hopefully do your paper justice. So to get started, would anybody like to give an overview of the paper? That's ideally not myself or Philip. Normally I would say not myself, Philip, or Quinn, but Quinn's unfortunately out sick today, so she really wanted to make it, but such is life. So, but yeah, any volunteers?
I'd be happy to give it a shot.
Great, thank you.
So the three major pillars of a correct CRDT is that it has eventual delivery, it has convergence, and it terminates, meaning all updates lead to execution that eventually completes. So the last criteria, termination, is kind of boring. You just get that by being, I don't know what the exact properties would be. Writing reasonable code might be the way to express that. But the other two properties, eventual delivery and convergence, are what makes CRDTs interesting, and in the face of Byzantine nodes is more interesting. So eventual delivery means that everything that goes into every update that is sent to one correct replica will eventually make it to all correct replicas. The way that's guaranteed is actually the same way that you guarantee it with a CRDT not under Byzantine conditions. That is, there's always between all the pairwise connections between nodes, there's always a graph that will connect one node to another correct node. So if you have that criteria, you win. But with the added caveat of one of the standard optimizations, or one of the standard ways you guarantee that connectivity is enough to get message delivery. The usual trick is you send, if you have as a single node, you have a set of pairwise connections, and you relay every update you know to every node that you didn't get that update from, is the standard protocol. If you just do that, you'll be fine under a Byzantine condition. But there's a normal optimization you typically apply to that, where you kind of keep about a vector clock of the positions of all of your peers, and then you compare, you use that to reduce the amount of state you synchronize. So instead of sending everybody everything that you didn't hear from them, you send everybody everything they need to catch up to your vector clock. That doesn't work under Byzantine conditions, and that was kind of the key notion in the first part of the paper, or the section of the paper describing the eventual delivery guarantee. The solution to that actually kind of comes up when we talk about the second criteria of a CRDT, which is convergence. And that is a correct replica that has the same updates as another correct replica will always have the same state as that replica. So the suggestion of the paper for how you guarantee that is you create a dependency graph between updates. Like, let me rewind to what the challenge is here. So if given an update, you can accept or reject it using only the update itself, meaning you can just examine the update, not consider your own state, but just examine the update and accept or reject it. Then convergence is easy. But a large set of interesting CRDTs require you examine your own state before you can accept or reject the update. And that's where convergence becomes a more interesting problem. So the proposed solution is to, with every update, convey its effectively its in nearest dependencies. So if I apply this update and I depended on this prior update to make the decision or to create the update, then I include basically the name of that prior update. The way they suggest doing that is by hashing your update and including in the hash of the prior updates, basically forming a Merkle tree. So put all your updates in a Merkle tree so you have a dependency graph between them all. Then you can, if you're a participating correct node, given an update, you can know that you're applying it consistently if you have its priors, the set of updates that came before it. As long as you have that, you know your state is the same as any other node that's applying it. And then you can apply it given that state, and you're correct. So with that, you guarantee convergence. You can also use that knowledge of the priors of an update to have another way to optimize for eventual delivery. So the dumbest thing you can do, to recap, is just send everybody everything you didn't get from them. But if you have this Merkle tree lying around, you can find your, with the peer you want to synchronize with, you can find your closest common ancestor and synchronize everything after that ancestor to where you are now. And that gives you a simple strategy, a lot like Get. Yeah, so I think my reading is the big insight of the paper is that if you build this dependency graph among your updates, this Merkle tree, it actually never uses those words, which kind of surprised me, but maybe I'm using them incorrectly. If you build this dependency graph among your updates, then you have a nice optimal way to guarantee eventual delivery, and you get convergence. And as long as you have the three key properties of a CRDT, eventual delivery, convergence, and termination, you're good to go. And the paper, it's fairly convincing that you can get those three things with just this Merkle tree.
Awesome, thanks. Sorry.
I'd love feedback on how illuminating that description was. First time I've tried to say it out loud. Cool.
I think it was very clear. Very well done.
Yeah, so on the why it's not called a Merkle tree, I think maybe because that's such a broad class of thing, right? So if you have it doesn't say anything about how it's sorted, right? So this is specifically a dependency graph, as opposed to, say, just a set of things by their content hash. He does mention late in the paper, that there are systems like this, or that could be implemented in systems like IPFS and a few others, which don't have, necessarily this, binary, sorted tree sort of property. So that might be one reason why. And we can add that to the list of questions to follow up with Martin on as well. But yeah, I agree. I think that's a really lovely summary. Since you mentioned vector clocks, so I did a little poking around, and so we're actually trying to implement this at my company at Fission right now. And we're bumping into a few things, and just to kind of like get some of the conversation started, does anybody have thoughts on like some of the downsides of this approach, as opposed to something like a vector clock?
Well, it's about knowing what exactly is missing from your set. You're talking to another node, and you have some changes, the other node has some changes. What's missing? It's a bit anyone's guess. I would probably do something probabilistic with Bloom filters to get a first approximation or something like that. But or in some cases, if I know that I'm missing changes because they're in the dependencies, that's easy. That's the easy case. But there may be things I don't know I don't have, and then yeah, I'd probably go with Bloom filters or something like that to coordinate. Hey, this is the stuff I know. What am I missing?
I think there's, compared to vector clocks, there's a lot more state you're keeping around. You've got this dependency graph versus just a set of hints.
Space, yeah.
Yeah, something like a mutable register, you have to run through every intermediate step rather than just saying, well, I know I can skip all of these, right?
Yeah, you're also like subject to all of the idiosyncrasies of hashing. So like you now need to figure out some ordering mechanism just for understanding like, cool, how does that dependency graph structured, which you can write into an algorithm pretty straightforwardly. But like, I think that combined with the, do I have all of these messages and the need for all prior messages is a really, really big overhead. It's a lot, like in practice, that means a single dangling message in your dependency graph can really grind things to a halt. And so now we have like a data availability problem. And so there's, you can see lovely threats where I issue stuff, turn Byzantine very quickly and decide to just not make that thing available that I published in the tree.
Philip.
Yeah, we're all talking about this thing, and I want to call out one part of the paper that talks about this. It's in section 3.2, like the second paragraph, where he says that our prior work presents optimized algorithms for reconciling two node set of updates via hash graphs. And he says that this can be very efficient, but then gives an example of something that has up to 3 heads, and you can summarize that in less than 100 bytes. But I find that a weird example because 3 heads may, well, for some CRDTs, be more than enough. So for example, I think, well, maybe to give the counterexample, let's say a counter CRDT doesn't have that much causal dependencies between the individual operations, right? So if you have a counter CRDT, you may have a lot of heads. Well, exactly the amount of count in your counter CRDT of heads lying around. So reconciling there needs like support for way more than 3 consecutive heads in your CRDT, I think. So in that case, it seems like that may become much more of a problem than described in the paper.
I think count might be an example of a CRDT that isn't state dependent to accept or reject, because at least as I imagine implementing it, you don't need to know the state of the counter to accept or reject. So I think it might be 0 heads. My understanding of the number of heads you need is it's related to the number of updates that could contradict each other, or like the width of a ambiguous change. I'm not phrasing it right. It's concurrency related, not.
Often it's cell creation, right? In many list CRDTs, you have to first create the cell in the list before you give it a value. So I think this is one of the clear dependencies, but yeah, you can still have a lot of heads, everybody creating cells, which are not interdependent. Or as you say, setting the value of a cell may or may not be dependent. Though I think adding arbitrary dependencies may help in that case.
Yeah, he says near the end of the paper, I'm trying to find it, but I can't right now, that this is really focused on op-based CRDTs instead of state-based ones. So the counter example, sorry, the counter CRDT example probably wouldn't work as well under this, because as Philip mentioned, it would have a very high fan out, right? So you could represent that in operations and have them be one after another, but that's also going to be more subject to more subject to this possibility where you're missing data and there's more of a data availability problem between updates, because you can reflect any state-based CRDT as op-based and vice versa, right? So, sorry, just because there's been a little bit of background noise, anybody who's not talking, could you please mute yourselves in the meantime? Marc-Antoine, you have your hand up.
Yeah, stupid question about, the disadvantage of not having sequence and this and that. Why not both? I mean, is there any downside, except space, of course, to not combining the hash and the time? You don't put the time in the hash, of course, but otherwise you put the payload, the time, the hash, and you have all the advantage of vector clock, like have a Lambert clock, of course, and the hash for security.
When do you decide to only use the vector clock in that scenario?
The vector clock is more useful for knowing what you're missing. As I said, that was a problem with the hash. It's like, okay, this is what I'm missing. This is what I need to ask for because I don't have it yet. Whereas the hash can be used for all the dependency aspect and the checking. I don't know. I'm just speculating.
Are you trusting vector clock values from peers?
As far as their own events, right? They're saying here is my clock of my events originating from them, not the events they're supposed to transmit.
Right, and that can be lied to about, right? Like it's really straightforward to construct a DAG and IPFS that lies about its file sizes is a great example where the byte count itself is effectively gossipy because it's not verifiable via a hash. And so you have you don't have the property of being able to, like, I can just give you, oh, my clock height is 25 million, deal with it. And now you have a problem on your hands about, and so you just can't trust any of those clock values in a Byzantine context.
What I'm saying is that a problem? But yeah, I can see how it is because it forces you to up all the clocks.
You can mess with it, right? I can write a faulty client that sends you.
Oh no,
bad
that's obvious.
values.
Yeah. But I'm thinking, what's the consequence? Yes.
I mean, you could take the vector clock as an optimization and like trust it in the meantime. And while you're trusting it, verify the actual hash-based kind of structure. And
that's
see whether it matches up with the vector clock. And so, like, eventually, you're trusted in the hash-based kind of structure, in the Merkle structure. But in the meantime, you may use the vector clock that may be incorrect as an optimization.
And it's actually a way to discover some Byzantine nodes. Yeah, it is in the line of where I was going. Like, use the hash, but use the clock too, especially to know who's what you're missing. And yeah, I think also the other thing about Lambert clocks is if there's a huge delta, it's suspicious. So you can constrain the delta value, right?
I mean, you can, but that could also then block legitimate rights if let's say it's been offline for 3 weeks or something. You're right though that there
mostly delta into the futures. I didn't mean delta into the past.
No, but even deltas into the future, right? Yeah, you have out of order message delivery because it's a distributed system. Yeah. But you're right that there are these, and they're not Byzantine tolerant, right? Fault tolerant. There are some hybrid logical clocks that take a timestamp and a vector clock, and you can normally trust the timestamp if it arrives within some window of the present time from the receiver, and if it's outside of that, then you fall back to the vector clock. But that's definitely not going to be BFT.
I'd love to go back into like the discussion about the heads in an up-based CRDT. And I think I may not have like the correct picture of what would be a head in this kind of system. So maybe that's something that someone may help me explain.
In challenging you, I realized I didn't understand it either. So I'd love that as well.
If anyone wants to jump in, but before I do, Quinn and I have studied these independently. So, okay. So you can describe any CRDT as a graph of updates and dependencies between them. And if you have some structures, like a counter, the example that Philip gave earlier, there's no dependency, there's no strong dependency between any of the updates, right? There's no required dependency between them. So you can just say, well, here's my CRDT as a root node, and then a whole bunch of them sticking off of that in your graph. Very, very high fan out. That's one way of doing it. Now it's very state-based. If you want to do a op-based version of this, then you can create a timeline of, and then I added this and this, this and this, even though there's nothing special about the order that they're coming in, right? You can force them into an order and then create this, this deeper DAG structure from that, and then say this came after that. But the actual underlying, like the dependency between them isn't there. So that is often better to be described as a state-based CRDT, just because it'll be much more efficient to do the reconciliation, and you don't have to replay. If there's some change earlier in the DAG, you don't have to go back and replay over everything. You literally just count how many are in there. Yeah, and so that's where you get that very high number of heads. Something that we've been playing with related to this paper is implementing CRDTs as data log, which gives you graphs, exactly this. And we're finding that the description of state-based and op-based tends to come down to this. State-based ones tend to be a lot shallower than op-based ones, which tend to form, not necessarily just a linked list, but some much deeper, longer structure on average.
Okay, that was very helpful.
Yeah,
And
thanks.
maybe to give another example, like RGA, or not to give another example, but to try to come up with another example. In RGA, then every time you insert not at the end, you may generate a new head, wouldn't you? Because that will then refer to the previous element as a hash. And so I don't quite understand why this example in the paper is like, yeah, you can have even 3 heads, because you will likely end up with thousands of heads in the RGA case. I guess that's what's really confusing me. There must be some way of, I don't know, reducing the amount of heads or something.
Yeah, so it depends also if you're flaring out, or you're fanning out or fanning in too, right? Like what is the data dependency on the fan in? What are the literal things it depends on? And that's probably going to be fewer than.
I think if you're, okay, you have this linked list and you add something in the middle, and that creates a new head. But if you add something after that, it depends on the previous one. So you can make that the new head and forget about the previous mid insert. So there can be many mid inserts anywhere in the middle, and that's a pretty big fan out. But at least once they become contiguous, it creates a dependency. I'm also thinking, is there a benefit to having some soft dependencies, saying, this is not an absolute prerequisite, you don't have to wait for it, but this is one of the predecessors, and you're making the graph more graphy, like at least, for example, your own last operation, right? Again, it may not be an absolute predecessor, but distinguish, this is a hard requirement, don't try to apply this. And this is just something that came not long ago that you may want to be aware of. And it may be a way to reducing heads, actually, making it a point to create an artificial dependency. Of course, it creates a bit more contention. You lose the fluidity of the order independence, but you gain connectivity and robustness. So there might be an optimal trade-off there. And if you mark which ones are explicit, are necessary, and which ones are soft, it could be. I'm again speculating here. I have not tried this at home.
That is a very good point. And I just remembered another part of the paper that actually, like, well, it kind of says you can do both. You can do either one. You can either create lots of heads in the, for example, in the RGA or in the counter case, but also you can just add more causal dependencies than strictly necessary. So there in section 3.1, constructing a hash graph, it's saying every update U contains a set of predecessor hashes. And then later, this may include the hash of the last update generated by the same node, as well as any hashes of updates received from other nodes since the last update. And so that is not like, he's not saying include the causally dependent elements, just include everything you've seen so far.
Well,
and that helps reduce
at least causally, and that's why I think it'd be nice to distinguish.
Yeah, exactly. And that's like a super interesting distinction, because if you add as few as possible, so only the causally dependent things, then peers would strictly only have to wait for all of those causal dependencies to be delivered. But if you include everything that you've seen so far, then another node that receives this update with all of those causal links will wait for all of them or all of the other mentioned causal links to resolve before accepting this thing, which is like kind of a trade-off, and it might be super useful to separate those two cases.
But I don't think it's an arbitrary choice, right? So RGA, using the example from earlier, Martin has actually a couple really nice papers on improving some edge cases in RGA. And that really is about the causal dependency of where, for example, you're typing in a document, right? It's not just like at the end and then I'll refer to something else. It's like literally the link goes here because I'm going to start typing right here in the doc. And then having a mechanism to say, well, we're going to order them maybe based on the hash to put them one after another, and you get really good versus user expectation that chunks of text will be separated based on the writer. Or at least based on their causal dependencies. So I don't think the choice is completely arbitrary in here. It really depends on the CRDT. But there is maybe a Byzantine case where somebody starts, typing random garbage in the middle of the document and saying, yeah, sure, I'm totally dependent on all these things. If you start to say, well, everything that I've seen, this comes after that, you might potentially open, like the CRDT properties will still hold, but semantically it'll be wrong, right?
I'm very curious about why we're not publishing Bloom filters of every message we've accepted, going back to Mark. And I think a little bit of your recent excitement, Philip, on set reconciliation across multiple peers. To me, that feels like an optimization that might be missing here, or might be worth sort of considering. Being able to just like actively check messages that I have against other messages might help. It's definitely an optimization of this fundamental, but
Philip?
So it's actually one of the previous papers of Martin. It's on this page. You can see on the right, our prior work 23 presents an optimized algorithm for reconciling two node set of updates via hash graphs. And what he's doing is actually constructing Bloom filters. However, he is not constructing Bloom filters in a way that I've been so excited about recently, which is like without context, without prior context. But it's like instead of a vector clock, you store a Bloom filter of all of the hashes that you send some other node. So it's just an efficient way to remember for yourself what you synced with a known peer. So yeah, he's kind of doing something like that. And I would love to see more of the more general case with like syncing with nodes that you had no prior context with.
Syncing nodes with no prior context with Bloom filters, super interesting. There's a couple of problems, right? So the first obviously is you have to make sure that your false positive rate is fairly low. And as the size of this graph grows, the size of your Bloom filter is also going to grow. So if you have trillions of updates, your Bloom filter has to get pretty big. And synchronizing, along with your messages, hey, here's a gig as well of this giant Bloom filter, isn't as helpful. Yeah, so that's probably part of why. And then the false positives as well, which sound like, which tell the other node, hey, I think I have the stuff, don't send it to me. But it's like, well, I actually do need it. And there are ways around that. There's in both hex bloom and the invertible bloom filter, they have redundant fields, so that if one hashing mechanism fails, you have a fallback, but that's completely off topic. So we can have an entire other, in fact, maybe that should be next month.
I saw an article about growable bloom filters, like bloom filters that grow as you add elements and scale to the number of elements to maintain a probability. But yes, it is another topic. But I am a good question by Brendan, like keeping a bloom for all the peers can also mean a non-trivial number of bloom filters that you're keeping track of.
Which is actually something really nice, like even with the downside of needing data availability with this current, technique under discussion. It doesn't require tracking what everybody else has necessarily, right? It's like it's literally unbounded and trustless, which is amazing.
Yep. It is amazing. No, it's the technique is absolutely brilliant, as Martin's getting us used to.
And I wanted to add that in the work he presents in 23, I'm not 100% sure, but I think these bloom filters are only tracking the heads that you send some other node. So once you create new heads and send new heads to the other node, you'll again re-encode your heads at that point, that kind of snapshot, as a new bloom filter. And thus, like the elements in the bloom filter are very small, and usually, like if I now thinking back to all of how those causal links work, I can see them, or the set of heads, being like a 2-digit number or something at maximum. So, or depending on the use case, I guess, but still.
There was one thing I noticed with the heads, and they kind of called out to it, where they said, like, I think it was the number of heads. It was
NA, I think your mic got very quiet there, at least for me. Anybody else? I could hear typing, but not words.
Oh, did you have unclack activated?
And I'm not sure whether the typing was from NA. It might have been from someone else.
Okay, well, while NA figures out, classic Zoom audio issues.
I think I figured it out.
Oh, great. Okay, please.
I had for some reason my microphone volume got turned all the way down. There was somewhere it pointed out that the algorithm was still correct, even though it was possible, I think it was to create a lot of heads. And that seemed like sure, cool, it's great that the algorithm is still correct, but that seems like it's still kind of a problem if a Byzantine node creates like 1 billion heads and now you need to keep track of them, and like that becomes an issue. Is there, I don't know, techniques for analyzing that formally or mitigating it or anything? Or is it just you need to have a little heuristic going that like notices if someone's spamming you with 1 million heads? It's like, you're probably not legit.
Like, isn't that just rate limiting?
I suppose it is.
Like, we just, hey, stop dialing me, bro. No more messages.
Yeah, I think so as well. Like, and I'm thinking of I love the last or one of the last paragraphs in the paper, like before on that page on the bottom left, on the very bottom left, where he's comparing the operation-based approach of this paper to the state-based approach in the Merkle search tree. And I think like in that case, you would essentially get an update for a Merkle search tree from someone else. And there it's even more literally rate limiting. You get like, you realize that the update's going to become like maybe a couple of megs in size, or maybe a gig in size. And you're like, I think I'll stop listening to you now. You don't seem to produce an update for me.
I think the other really interesting thing in this is, even if you say, I'm not going to listen to them, if it's a legitimate update, it's probably still going to get back to you in the network, assuming that there's enough other peers, right? And so it's like, you don't have to have a direct link to everybody else. It's just what's filtering through the network. But there are a few of these cases, right? It's like, there's a lot of heads, or I'm getting a lot of updates where I don't have the intermediate dependencies that would connect it to my graph. Or, like there's a few of these cases that are like, oh, that could be, a lot of bookkeeping. But also, if I just drop them after, say, 5 minutes of not getting the intermediate nodes, maybe that's not the end of the world, because I'll hear about it again.
Actually, that's an interesting point. I think that if you had this case where you're not accepting an update from some peer because it is too big, and then it makes its way around the system, and there are some peers which accept this big update, and they come back around to you, then you stop accepting updates from them. So it feels like if you build in, or if you model rate limiting in your CRDT model here, then you may get some kind of network split where the nodes don't converge because there are some nodes which have a higher rate limit than other nodes. And so there's like a split network of one set of nodes that use the bigger thing, whatever it is, more heads or a bigger state-based CRDT or something like that. And there's another set of nodes that just stop accepting messages from the other part.
Yeah, but you should always be able to take two of these structures and mash them together. And like, I mean, it might not be performant, right? But like, and then replay over it and get the same state. The only guarantee it gives you is if you have received all the same messages, you'll converge to the same state. And at least in concept, you could diverge for 50 years and then still come back. Whether or not that's practical is another question. Mark and Fawn.
But remember what we said, that it's easy to create an update that narrows the graph. So if you have something that has tons of heads, it's easy to create updates that refer to many heads, like say a dozen heads, and then do that hierarchically, and you have very few heads after very little time. And you distribute that, and then the other partition will pick it up. It's not the number of updates, it's the number of heads, and that's easy to reduce if you make it your goal.
Don't you still need all of the the causal dependencies eventually, and so you still end up needing the bit where the graph goes out like 10 million heads wide and then comes back down?
Yes, but it's not the message passing is a few heads. That's the point. And
Okay.
Then you realize you needed 10,000 things, and then you have to negotiate that. Fair enough, but at least you know what you're missing, and that was with little bandwidth. And that was the point.
Jumping back a little bit to Bloom filters and finding ways of doing reconciliation. I wonder, because in any of these graphs, we also get transitive closure, right? So if two nodes share some subgraph and they can negotiate where that point is, they don't have to talk about anything below that point. And so maybe you could start finding more efficient ways of sharing, well, we know that we're at least up to here. Here's the Bloom filter of just the updates since then. Have you seen any of these? Things like that to really narrow it down. And so that's not without prior context, which is the stuff that Brendan and Philip were talking about earlier. But it might be an interesting approach.
And even I think when you're missing something that you're missing, you don't have to send them all. You can just send a Bloom, and you'll get maybe some more messages you already have. Big deal.
There are also some nice techniques where you put Blooms into a Merkle tree, and as you work your way down the tree, there's fewer elements in the bloom, basically, and you can have like differently sized blooms as you walk
Okay.
down. Which isn't, yeah, basically then you don't have to go all the way down, and you know, well, I definitely have these siblings to this node, right? And so it's like I'm missing stuff over here, and then you can check against the bloom filter. But now again, we're back way off topic. I think we need to read one of these papers next month.
That sounds good. The No, I really think it would be interesting to see if the question is how many non-causal links do you want to add and what proportion. I think there's certainly a sweet spot to find there that might be easier to find empirically than theoretically. And I think it'll depend again on the CRDT structure under consideration. I'm curious because you got us to read this, and you mentioned the upsets paper, and I read the upsets paper, and I'm curious how these things combine, right? There's all this wonderful stuff that Martin's doing, and it's like, okay, can I mix this and that?
What is the upsets paper?
Wow. Feel another question while I find it.
There was something I was a little curious about, and I might have missed discussion about it as I got web zoomed. But in the system model, they say that nodes that are neither crashed nor Byzantine are correct, and then all of the properties apply to correct nodes, and we just ignore our Byzantine nodes because we don't care about them. But I think also they said that like even hardware and software faults, like just bugs and cosmic rays, count as Byzantine behavior. So doesn't that mean that like, and the system model doesn't account for a node becoming Byzantine, like nodes either are or aren't Byzantine, sort of implicitly. So doesn't that mean that like all of our guarantees kind of go out the window because like cosmic rays can screw us over, or there can be a bug, and all of our properties only apply to correct nodes, and cosmic rays and bugs mean that our nodes aren't correct, they're Byzantine.
So in Byzantine protocols, it's not that they're in two separate boxes completely. It's you can switch back and forth, typically. And so in, for example, Byzantine consensus protocols or early BFT consensus protocols, you need to have at least a third at any given time, or sorry, less than a third at any given time are Byzantine, right? And so software bugs, cosmic rays, all of those things are accounted in that 1/3. The argument here is somebody could still have a Byzantine node that's writing garbage into the middle of your collaborative document. And that's bad, but it's not breaking the protocol, right? The guarantees that we're setting out by the CRDT itself, it'll still converge. If you have a Byzantine node that's doing things that don't follow the protocol, they won't get applied to any of the replicas. And that's the argument. So even if there's a software bug that only shows up once every, I don't know, once a year, it will then be temporarily Byzantine and then come back to following the protocol.
Okay, that makes more sense. And I sort of figured that might be the case, especially because when I like took notes about this, one thing that I noticed was it also points out that nobody knows whether a node is Byzantine or not, and that sort of feels like it kind of accounts for that as well. But okay, yeah, that makes more sense.
Yeah, it's even worse in, or I guess a weaker claim, or stronger claim. I'm not sure which way it goes in this case, where we're not even tracking who's in the network at all, right? We just have some links locally to your node, but we don't know how many participants are there. Are they always online? Are they coming on and offline? How many of them are Byzantine? How many of them aren't, right? Like we know nothing about the structure of the network at all, right? Which is actually, again, really amazing, right? That makes it very convenient to apply something like this. Now, again, there's, these cases where you have, 500 million concurrent heads that you have to reconcile, but you can also reconcile them a little at a time, and that will still converge.
That's actually interesting. I wonder if it's possible to focus on a region of the graph, right? I'm in this part of the document. Can we reconcile this first? It should be possible to do that, actually, to optimize, to direct the reconciliation towards my active region.
Yeah, so we've looked at this a little bit in, so at Vision, we have a project called the Web Native File System, which in the latest update is a CRDT. And one question we've had is, well, how are we going to, let's say that you have more than 2 concurrent updates, how do you reconcile them? Because any other node could reconcile them too. And they could be, they might not have seen all of the branches. And so doing them always pairwise also falls over because you might be reconciling them in different orders. And so your semantics have to not take into account only merges, right? Merges are almost like a special thing. And any ordering of those is considered to be commutative under those rules, right? So it's like you do need some special sauce for that until you start making updates again.
Very interesting. And that's useful and makes perfect sense.
Awesome. So we have about 10 minutes left in time here. Is there any final points, questions, discussion that people really want to get through live here?
I'm curious about your implementation story. I mean, what were your obstacles? You've had your hands in this much more than any of us.
Well, I would actually say Philip has had his hands much more in this. So I've been essentially, writing specs for the collective us. Yeah, I've been mostly writing specs. Philip actually has to go and then implement it, right? So we have 2 systems. One is a file system. Another is upcoming. It's a data log. So it's a database. And they both implement, or the file system is about to also implement these ideas, right? And the database definitely implements this stuff very deeply, actually, literally with the intention of being able to support arbitrary CRDTs, which is another Martin idea from a few years ago that he sort of offhandedly says in a presentation. We're like, I wonder if that would work. So yeah, we've run into a few things like, what's the order that you do reconciliation in? And as long as there aren't updates, does that matter? That's one. For the data log, we found that, yes, we get these because as soon as you start modeling CRDTs the way in the paper, you're describing graphs, right? So data log happens to be a really nice way of describing graphs, and every fact in that database is content addressed. Therefore, it has some way of pointing at it. And we've found that having those direct pointers, those causal pointers, is useful, but so is having just like an entity ID and saying, well, these all belong to a set. There's no order, right? And mixing and matching those has actually been very fruitful. And we can do things like implement transactions directly using graphs, right? Like this, which is interesting. Yeah, but so basically this all ends up being very fruitful. Our biggest challenges have been, what if you don't have the intervening or the intermediate updates, which is something that we really miss from vector clocks, especially in the database. Because if you have a mutable record, or mutable register, it'd be nice to just skip everything in between, but we haven't found a really good solution to that yet. Other than there are some techniques. So Quinn found a paper on typical binary pebbling. And so she sort of adapted it so that if you take the closest hash with, let's say, zeros after it and say, well, that's going to be my anchor in addition to the pointer, that might give you at least like some better jump in between. But that's not Byzantine fault tolerant, because you could put that, like it could just be a complete garbage node.
And what about the combination of clock and hash?
So it has the same problem. What's your source of truth? Right.
Yeah, well,
so you always have to check.
You always have to check, of course, but the clock can give you a shortcut.
Yeah, so it can give you an idea of where you might want to search, but you still have to go and find the path, which is, again, at least for the data log, that runs very, very quickly. The database, the file system has a harder time with that, because you actually have to find the relevant node and reconcile within that. Because the database, all of these items are just held as a set, so we can just sort them. File system, you have versions that come one after another, and you say this is the history, right? So you actually have to play over that history to find the relevant chunk.
Of course, of course. Yeah, I'm trying to understand. I'm not sure I understand the problem fully, in the sense that when you say you have to find the missing intermediate value, they would be given by the DAG dependency, wouldn't they?
Mm-hmm. So I have node A, sorry, let me reverse this. I have C, which depends on B, which depends on A.
Okay.
And I have no way of getting B. I don't know that I depend on A now. Correct. So if I don't have access to B, I don't have access to some intermediate dependency in this chain, I have no way of knowing that there's this nice transitivity down to A.
That's correct. But then, I mean, basically, C is anyway, you're missing your dependency, so it's kind of in waiting state, because until you get the intermediate. So that's fine. You don't need to know that it depends on A. You just need to know it depends on B, and when B comes, then you'll know you'll depend on A. But you're not applying it until you have B.
Right, which is potentially a data availability problem. If nobody has a replica copy of B, I'll never be able to apply C.
That's correct. Yes, the question is, what about lost IPLD records, I guess, in your world?
In our case, yeah.
And this becomes a question of redundancy. Can you have, and that's why I was saying maybe give the absolute dependencies and some extra random known dependencies, and you can give enough of those, and there's probably a threshold where it becomes possible to skip missing chunks with some probability.
Only when it's not Byzantine. Because these skipping could be in a completely different part of the graph in a faulty node, in a message from a faulty node.
Yeah, but what I'm saying is, if you have enough extra links, the extra links could, among other things, skip over the part you don't have and give you these dependencies you're missing. Like I'm even thinking, in log files, you give the 5 minutes ago, you do kind of multiplying the time by a certain factor at each branch, so you know which log files to prune. So in the dependency graph, you could say, give something very recent and add sub-dependencies to various orders of magnitude of older things. So you have these, I'm speculating. I don't know if that would help at all.
The core problem is you need a single source of truth. So if you walk back in single steps, or walk down the causal links in single steps, you should get back the same kind of link eventually that the skipping link, the skipping causal link from the topmost node gave you. But what if it doesn't? Which one do you trust now? Or do you throw away the node in that case altogether? If you throw away the node in that case altogether because it's invalid, then you can't just assume that the skipping link is correct without verifying it over the single stepping links. It's about the source of truth, I think.
Okay, let me take it from another angle then. And I don't know if this has any value, but you've lost B. Then C, it's hard to validate because you've permanently lost B. Couldn't you say, listen, I'm going to send a message that C has become problematic because we've lost B, and whoever has created C should give me a C prime with a different dependency that does not depend on B. And they should know what another dependency could be. Is that a reasonable strategy?
That seems like it might not be possible if C actually literally causally depends on B. Like it is a change in the state to the object that B is describing. And so you need to apply the 3 updates in order for the...
No, that's absolutely true. But what I'm saying is if B's totally lost, then C is totally useless no matter what, right? Knowing that it ultimately depends on A doesn't help you. So the question is, now that we know C is useless, how do we recover a reasonable state, given that a loss dependency has made all downstream events problematic? What do we do then?
Yeah, so I think you don't have a lot of choices, right? Like you can't apply it.
Exactly what I'm saying. So you can't apply it. And so
Yeah.
I don't see that as okay, then C is made invalid by the loss of B. Okay, what then? I mean, then you ask whoever created C to give you something else. And you tell them C has become useless. What else do we do? And I don't see that as a protocol problem. It's a data loss problem, corruption problem. It's like the cosmic ray problem. You've lost something. You've lost something. You need to fall back somehow. But I don't see it as oh, how do we route around the lost thing? Because C has practically become useless. Give up on it.
Well, it's become useless for some partition, some group, right? And you might hear about it 10 years from now or something, right? So adding that new link might create more garbage updates for somebody else. I guess the question is, practically speaking, does it matter, right? As long as there's a lot of connections coming in and saying like, well, I have more than one dependency. If this is a straight line, that's a huge problem, right? But as long as there's some other fan out happening that's then getting fanned in over time, you'll find some path back. You might just be like really out of date, but that's kind of the point of CRDTs, right? So there's a question of like, well, how practically important is it?
I think it's an interesting kind of thought experiment, and it also connects a little bit to the Byzantine fault case that NA has been talking about before. Like, let's say there is some kind of data corruption or something, and you're on some kind of replica, and that incorrectly assumes that B's hash is something where 1 bit was flipped, so it's an incorrect hash. And it tries to tell that everyone else, it itself assumes that everything is correct and just includes it in its, I don't know, in its view, essentially, right? But all the other nodes know that it is incorrect. When does it actually decide to check itself again, to like double check itself, right? Wouldn't it be nice if the user in such a case at some point had their app say, well, I think no one is accepting my updates. Let me recheck all of my updates. And if it turns out that I have some kind of corruption, I regenerate some of my updates. Maybe that's something you would want to do practically.
I mean, it probably depends on the application, but you know, again, just like taking from a general point of view of just CRDTs, you should be able to run entirely in single user mode offline for years and then reconnect and have everything stitched back together. Whether or not, again, whether or not that information when it's stitched back together is like meaningful is another question, right? It's like, well, I've been writing a book with 3 other people and we haven't synchronized in a year. Yeah, the book's pretty different, right? For, you know, the different chapters. But at least we all see the same view and then we can go through and correct it now that we're synchronized, right? So I think we might have to lean more on the user a little bit. there's a nice recent, another recent paper from Jeffrey Litt called "Sync What You Can, Fork What You Can't." That's essentially about this, to say like, well, I have my updates. I don't want to lose stuff. I'm going to fork this part of the program. Anyway, sorry, it is now past the half-hour mark, so I'm going to stop recording. Thanks everyone for coming. We'll probably hang out for a bit of an after party here and chat a little bit more, but